In this course, we'll often use the following control system configuration. This is the one that we had obtained after the balancing stick example. The block P stands for the process, and this process is described by the transfer function P of S. We have left out the S dependence to simplify notations. The process input is MV, so the manipulated value. The manipulated value is the value you can act on to influence the system output. The system output is PV, process value, and it is the variable that is controlled. There are in general two other undesired inputs that are affecting PV. This is why these inputs are called disturbances. Disturbances at the input are called load disturbances, DL, and disturbances at the output are called disturbance values, DV, or output disturbances. The block C stands for controller. The controller is described also by a transfer function C of S, and again we have left out the S dependence for simplicity of notation. The role of the controller is to control the output PV, and as you can see, a negative feedback is used, so the controller is using minus PV. It is acting on SP minus PV, that's the control error E, to compute the manipulated value. In some cases, we will complexify this control system configuration to take into account the disturbance dynamics for systems such as the LTR 700 system or the TC Lab system. So what we'll do is take into account the disturbance dynamics, right? Here we have written D. Again, I have left out the S dependence for simplicity of notation, but of course here behind this D is of course a transfer function D of S. And at the output of this dynamics, well, you have a signal that is kind of perturbing PV. At the input, what we have is really dV minus dV0, so the deviation of dV with respect to its nominal value dV0. This kind of extended control system configuration will be used in section 4 when we talk about feed forward. What we'll do is, for ease of notation, for simplicity of notation, simply write dV. But of course we have to remember that in the background the actual signal that is entering the disturbance is the deviation from the nominal point dV0. The implemented control law is MV of S is equal to C of S. That's the transfer function of the controller acting on the error, so acting on E of S. And in this course, C of S, the controller will always be a PID controller. We'll come back to that later in section 4, but the transfer function of a PID controller is like so. So it's KC, that's the gain of the controller, 1 plus 1 over TIS plus TDS over TDFS plus 1. And you can already recognize that there are 3 actions. This one is the proportional action. You can see that the output is proportional to the error through this term over here. This is the integral action, right? Because we have a 1 over S, and 1 over S, that's an integrator, and here we have the derivative action. So if you concentrate on the numerator over here, you can see indeed that we have a derivative action over here. So in the beginning of the course, we'll simply write C of S, because we have not yet talked about the PID controller, but later on in the course, C of S will become this transfer function over here. Well, what you see here on the screen is the control system configuration that we have introduced before, but we have added a signal N, which is meant to mimic the effect of measurement noise. So this is the actual PV, and this is the PV that is sensed, that is coming from the sensor. So it's the actual PV plus measurement noise. So what we can do now is compute the closed loop transfer functions. Well, notice that this system has two outputs. The first one is PV, the second one is MV, the output of the controller, and the system has four inputs: the set point, the load disturbance, the output disturbance, and the measurement noise. So now we can look at the relation between these four inputs and these two outputs, and this is what you obtain. And the first thing that you have to understand is how to read this equation. Well, the process value is this transfer function acting on the set point plus this transfer function acting on the load disturbance plus this transfer function acting on the output disturbance and this transfer function acting on the measurement noise. And you have something similar, of course, for MV. It's quite easy to obtain these relations. Notice that each individual transfer function, let us take this one, can be obtained by setting all the other inputs to 0. So here this is the transfer function from set point to PV. So what we'll do is set this one and this one and this one to 0, and we'll have the relation between PV and SP. Let us do this. So we'll assume that this one does not contribute, this one does not contribute, and this one does not contribute, and we are interested in the relation from set point to process value. So we are not interested in the manipulated value, right? So let us write this relation. So the output is PV, it is P acting on C, so PC acting on this signal over here. That's the error signal, but the error signal, that's SP minus PV, right? So we can write this as PC set point minus PC acting on PV. We take this one on the other side, and we have 1 plus PC acting on PV is equal to PC set point, right? And we have indeed that PV is PC over 1 plus PC acting on the set point. Well, let us try to find another closed loop transfer function, for instance the one from DL here, the load disturbance to MV. That's this transfer function over here, and we can obtain this transfer function by considering the second equation and setting the set point dv and n to 0. So we'll forget about this, this, and this, and we are not interested in PV, right? So MV, this is C acting on minus, there's nothing here, and then we have P, and P is acting on, well, DL plus MV, right? So this we can rewrite differently. We can say that it is minus PC. We are working with systems that are single input, single output, so we can change the order of P and C. So it's minus PC acting on DL, minus PC acting on MV. I take this one to the other side, right? And we have 1 plus PC MV is equal to minus PC DL, right? So indeed, the relation from DL to MV is this one here, minus PC over 1 plus PC, and this is what you obtain indeed. So you have to be able to do this to compute each closed loop transfer function from any input to any output. Now that we are able to work with closed loop transfer functions, we might ask the question why we want to control a system using feedback. To answer this question, we'll look at the alternative to feedback, which is, well, setpoint feedforward. The idea is to construct a feedforward controller in such a way that PV is equal to setpoint, and this can simply be achieved by taking as feedforward controller simply the inverse of the process, but this might lead to problems because this inverse might not be realizable. For instance, if you have P of S is equal to 1 over S plus 1, so this is a first order system, well, the feedforward controller is S plus 1, and this is not realizable because, well, this transfer function here for the feedforward controller must be proper. We have seen in the course Signals and Systems that the degree of the numerator is smaller or equal to the degree of the denominator. We'll have something similar if you have a delay in the process. We'll come back to that later. If there is a delay in the process, well, this delay cannot be inversed. This idea of taking the inverse of the process is going to lead to very aggressive control. This is simply because we are imposing PV is equal to setpoint, right? In this process we have some dynamics, right? And we want to impose the fact that PV is reacting immediately to setpoint. And well, because of this dynamics, this will require a lot of control energy, and in practice this will not be possible because in processes, well, you have something that is called saturation, right? We have seen in the LTR 700 process and the TC Lab process that, for instance, the manipulated value, the heating power, is limited to 100%. So what you could do instead of imposing PV is equal to setpoint is to say, well, PV is equal to some desired transfer function that you have to choose in an appropriate way, setpoint, right? And this is going to lead to a modified feedforward controller, which is simply T desired P inverse. And if you choose T desired appropriately, you can probably solve these two problems, but we will not go into the details of that. This is beyond the scope of this course. Well, we see also that our feedforward controller is based on an estimate of P, and we'll call this estimate P hat. We have to use an estimate because we do not know the actual process exactly. So Because of this fact, the relation between PV and SP is as follows. It's P hat inverse P set point, right? So in general, this will now be different from 1. Or if we use the other approach, and if we use T desired P hat inverse, right? Well, then the relation will be PV is T desired P hat inverse P set point, and in general this will be different than T desired, right? So this leads to the question of robustness, and we see here that if the process is changing, well, any perturbation on the process is reflected directly on the loop gain. So we see that this set point feed forward solution is not very robust in the presence of changes in the process. Of course, the process is subjected to disturbances, and set point feed forward is not capable of dealing with them. We clearly need a solution with feedback. Note that the idea of set point feed forward is sometimes used in combination with feedback, but this goes beyond the scope of this course. We'll see in section 4 that we can use a very similar idea to compensate measurable disturbances. Well, before we continue, this is a slide from the course Signals and Systems, and it tells you about the static gain. The static gain of a system is obtained by evaluating the transfer function at S is equal to 0. So H of 0 is the static gain, and it is the ratio of the output and the input under steady state condition. If this comes as a surprise, what you can do is review this in the version of the course that is available online. We have seen that using set point feed forward, we run into a number of problems. The question is, can we do better using this closed loop configuration? Can we do better using feedback? Well, this is our control system configuration with DL, the load disturbance is equal to 0, the N is equal to 0 as well, and we have seen that, well, the output of the process is linked to the set point and the output disturbance using this relation over here. We can see using this relation that if we make the loop gain PC large, well, this transfer function will tend to 1, so that PV is approximately equal to set point, and this transfer function here will tend to 0, so that PV becomes independent of TV. So we can kind of see here that feedback mitigates the effect of output disturbances. In fact, what is often done is to make the loop gain PC infinite at S is equal to 0 by adding or introducing an integrator in the controller. Remember that the transfer function of the integrator is 1 over S. We'll review this, but this is something that we have seen in the course Signals and Systems. So if we put an integrator in the controller, what we'll have is that the limit when S tends to 0 of C of S will tends to infinity. So what we'll have here, because of this infinite loop gain at S is equal to 0, is that the static gain of this transfer function is equal to 1, and the static gain of this transfer function is equal to 0, right? So this means that in steady state, right, well, PV will be equal to set point. This is what is written here. We obtain a perfect steady state tracking. PV tends to set point as T tends to infinity. This is really what we mean by steady state. C'est la réponse de régime in French. And this will be the case even if you do not know the process exactly, okay, because this controller has an infinite gain, and this will mitigate the effect of process perturbations. And you can see that we'll have this tracking, this perfect steady state tracking, even in the presence of output disturbances. We will see in section 4 that the controller that we'll be using in this course is KC, the control gain, 1 plus 1 over TIS plus TDS over TDF S plus 1. We've discussed this previously. This is proportional action, this is integral action, and this is derivative action. Okay, of course we'll review this, or we'll view this in detail in section 4, but you can clearly see the presence of the integrator in this second term over here, and we see here that this controller has an infinite gain at S is equal to 0. So this controller has indeed this property that it makes the loop gain infinite at S is equal to 0, and this integrator will ensure a perfect steady state tracking. Well, there is another way to see that the presence of an integrator in the controller will lead to perfect steady state tracking. For that, we have to look at the integrator system, right? And in the Laplace domain, we know that this system has a transfer function 1 over S, and by definition the integrator system integrates the input, and well, we kind of see that, for instance, if the input is positive, if you integrate something positive, well, then the output will increase, right? If the input of the integrator is negative, well, then the output will decrease. The only way to have something that is constant at the output is if you put something that is 0 at the input, right? So if you have something that is 0 at the input, well, the output of the integrator will keep its output constant. So the only way to arrive at a steady state, and a steady state means that all signals are constant here. This one is constant, this one is constant, and if you have the presence here of an integrator 1 over S in the controller, the only way to have something constant over here is to have here at the input of the controller is the 0 signal, okay? And by definition, if the control error, this is the control error, and this is set point minus PV. Well, if the control error is 0 in steady state, this means that PV tends to set point as T tends to infinity. In practice, there are two important types of control problems: disturbance rejection problems and set point tracking problems. In a disturbance rejection problem, the set point is constant or hardly ever changes. The main goal of the controller is to reject the disturbances, the output disturbances and the load disturbances. Well, a typical example of a disturbance rejection problem is the temperature control of a room. The set point, the temperature set point, hardly ever changes, but the controller has to reject disturbances, for instance due to people coming in and out of the room and disturbances coming from the outside temperature. Set point tracking problems are problems where the controller is designed to follow a reference or set point or trajectories as closely and as fast as possible. So for instance, the closed loop settling time is an important factor. Tracking typically occurs during operating point changes. Just-in-time production plays a more and more important role so that operating point changes occur more often and that the set point tracking plays a more important role. People have a tendency to associate the controller with set point tracking, but we'll see that the disturbance rejection capabilities of the controller should not be neglected. Control loop optimization is the art of finding compromises between disturbance rejection performance, tracking performance, but also robustness. Robustness is the sensitivity of the control performance to changes in the process. The control effort or control energy is also of concern, as this control energy is related to the final cost of the product and to wear and lifespan of the actuators. There are several control modes associated with the controller, and as I said before, this controller will very often be simply a PI or PID controller. Well, the first choice that you have is to put this controller in automatic or in manual mode. In manual mode, the controller output MV is directly manipulated by the operator. And this can be done, for instance, by changing a value MV_man in the human-machine interface to directly influence the process input. In manual mode, the control algorithm, and very often the PID control algorithm, will be bypassed. In automatic mode, the controller output is dictated by the control algorithm, typically, as I said, a PID control algorithm. Well, when switching from manual mode to automatic mode, the control algorithm output might be different from that of the manual output. So you have to organize a bumpless transfer from manual to automatic, and this means that the automatic output must track the manual output in manual mode in order to prevent integrator wind-up and also in order to organize this bumpless transfer. We'll see this later in the section on integrator wind-up. Another control mode is the output tracking mode, also called the interlock mode. This is for your information only. When this binary signal here, track on, is set to 1, then the controller output MV will track the value here, track val. This is a signal that can be chosen by the one that is programming the control algorithm. When track on is set to 1, the control algorithm is inactive, and as I've said, MV is equal to track val. I said that the control algorithm is inactive, but this has to be done in the proper way in order to prevent integrator wind-up. We'll see this later in the section devoted to integrator wind-up, in which we implement a controller that has this output tracking mode or interlock mode. An example of output tracking is the following. Assume here that there is a measurement PV that comes from a sensor, and that this sensor provides a binary flag to tell you if the measurement is okay or not. So if PV knock here is 1, this means that the measurement is not valid. Well, if this sensor is giving you this flag, PV knock is equal to 1, this means that the process value measurement is no longer valid, and of course you cannot use it for control. So what you should do is freeze the controller. This can be done as follows. You connect the PV knock signal flag coming from the sensor to track on, and you connect MV, the output of the controller, to track val. What will happen when the sensor flags a signal, a measurement that is wrong? Well, this one will go to 1 and MV will track itself, so that you have here at the output the last value that you had in automatic mode. Okay, so the controller is frozen with the last active value of MV. The controller is locked, and of course in the human machine interface there should be a warning for the operator to tell him that there is something wrong with the measurement, but at least nothing goes wrong in the sense that the controller is now locked. We have seen in the course Signals and Systems that processes can be well described in continuous time using differential equations, and when going to the Laplace domain, this gives rise to the concept of a transfer function. If the process is linear, the Laplace or S domain is also advantageous for controller design. The design controller is represented by a transfer function and can be, after inverse Laplace transform, represented by a set of differential equations. Well, in the old days, the continuous time design controller, this is the desired control dynamics, were approximated using pneumatic or hydraulic systems or analog electronics. Nowadays, of course, we work with processors, so we have to take into account the discrete time nature of the signals and the fact that the signals are quantized. Okay, we speak of digital controllers. The analog control scheme is illustrated here. The process here with actuator and sensor is described in continuous time or in the Laplace domain. The description of the process in the Laplace domain is used to design an analog controller. And as said before, in the old days, this analog controller was implemented using hydraulics, pneumatics, or analog electronics. The conventional analog controller is thought to be between the output PV of t and the input MV of t. Of course, nowadays we use digital processors to implement the controller. Nowadays, as we've said, we work with processors. They've become the standard of today, and they offer a number of advantages. One of them is, of course, flexibility. You can really decide to change your control law very easily. It's just a matter of reprogramming everything, compiling and downloading in the processor. Well, also you can implement much more complicated control laws, even non-linear control laws. You will see that control laws are no longer implemented using differential equations, but that they are implemented using difference equation. This is something that you will experience also in the associated control lab. Since the controller is implemented using a difference equation, well, the control law really is implemented on the basis of previous inputs, previous outputs, and it involves only simple operations such as multiplication and addition. In this slide, we present the overall digital control scheme. As you can see, you can recognize three parts: the digital part, the analog part, and in the middle an interface. Well, let us describe the analog part. We work in the continuous time domain, and the associated variable in the frequency domain is the S or Laplace variable. mv of t is the input of the system, and in general we have an actuator followed by the process. But in the sequel, what we'll do is neglect the influence of the actuator or assume that the actuator dynamics are included in the process. The process has an output PVP. We use PVP here to distinguish with PV that comes after the sensor and the anti-aliasing filter. So PVP is the actual process output. To measure the actual output, we need, of course, a sensor. We'll assume, in general, that the frequency response of this sensor is flat and equal to 1 over a frequency band that is much larger than the future frequency band of the closed loop system. Since the process output is going to be sampled, we need to use an analog anti-aliasing filter. This low-pass filter has to be situated in the analog part. This is very important. This anti-aliasing filter is going to remove all frequency components above the Nyquist frequency to prevent frequency folding or aliasing. In doing so, we obtain PV of t that is available for the interface. The interface has two inputs, so the first one is PVT, the second one mv of k, and two outputs, PVK and mvt. So if we start down here, well, PV of t goes through analog to digital conversion, so through a sample and hold, quantization, and finally digital coding stages, and this will produce PV of k. This PV of k is then used by the digital controller to produce mv of k. mv of k is at the input of the interface again, and it goes through a stage of digital to analog conversion. So we have first digital decoding and then a hold mechanism, and very usually what is done here is that a zero order hold mechanism is used in the hold mechanism. This is something that we have considered in the course Signals and System. So at the output here we have now mv of t, that is the input of the analog part. In the digital part, the signals have been sampled. They are discrete time in nature and they have a finite resolution because of the quantization step in the interface. We therefore work with digital signals available every kts, and the associated variable in the frequency domain is the z variable. Based on PVK and a setpoint SPK, the digital controller produces a manipulated variable MVK. Computer-controlled systems, as you can see, contain both continuous time and discrete time sampled signals. Such systems are often called sampled data systems. There are two approaches to digital control. In this 15-hour course, we'll only use the first approach, but I will give you an idea of the second approach a little bit later. So in this first approach, we start from a transfer function description of the process, and we use it to design a controller C of S, so that's also a transfer function. And in this 15-hour course, C of S will always have a structure of a PID controller. But of course, this continuous time controller, or this controller in the Laplace domain, has underlying differential equations that we have to approximate so that they become difference equations that we can implement on a processor. So somehow we have to find a description C of Z, because underlying this transfer function in the Z domain we have a difference equation that we can implement on a processor, right? So we'll talk about the PID controller in section 4, and we'll see in section 3 how you can approximate a transfer function in the S domain by a transfer function in the Z domain using numerical approximation. In this first approach, the analog controller designed by classical means is approximated, and we obtain a difference equation that we can implement on the processor. We have to increase the sampling frequency, so choose a TS that is small, to make sure that the output of the digital controller is as close as possible to the output that we would have had with the continuous time controller. If we choose a small TS, it means that also that the control signals will change slightly from one sample instant to another. As a consequence, these small changes in both the control output but also the measured output should be representable in the resolution of the analog to digital and the digital to analog conversion. This asks for a high resolution, many bits, so a small quantization step. And this small sampling period combined with this high resolution will of course cause a high cost. Well, we have seen that there is a first approach to obtain a controller in the Z domain that you can implement on a digital processor. You start from your description of the process, you use it to design an analog controller, and you approximate this analog controller by a digital control. We'll see later how to do this. And underlying here we have a difference equation that we can implement on a processor. This requires TS to be rather small, and small with respect to the main time constants of the process. There is another approach, and it is only for your information, that you can use with TS that is larger than with this first approach, and the idea is as follows. What we'll do here is obtain a discrete time description of the process, so a description of the process in the Z domain, but we'll do it in such a way that the zero order hold mechanism is taken into account. You might remember from the course of signals and systems that this zero order hold is introducing a delay of TS over 2. TS here is the sampling period, right? And if TS is becoming large, well, this is going to play a role. And in this first approach, this TS over 2 is not taken into account. But if you discretize the process appropriately, you obtain here a discrete time description that takes into account the zero order hold. And then you have to use a so-called direct digital method to obtain a controller C of Z from this description of the process in the Z domain. As I've said before, this is called direct digital design, and this is of course out of the scope of this course. If interested, you can have a look at the video course Digital Control. Process control can be represented as a hierarchy. Level 1 corresponds to base layer control. This level is also sometimes called the field level. These are the devices, sensors, actuators, proximity switches, on-off valves, and so on, that you can see in the field. The control that is associated is typically sequential in nature. Level 2 is the safety level. It involves environment and equipment protection. Safety instrumented control systems, so for example safety PLCs, that are physically separated from the general purpose control system, monitor the system and intervene when dangerous situations arise. Level 3 involves process control for single loop systems and multivariable systems. In this 15-hour course, we will only consider level 3A and stick to PID controllers and feedforward. If interested, the video course Practical Process Control will take you further down level 3 and explore some parts of level 3B on multivariable control. Level 4 implements more advanced types of control that involve real-time optimization. One such method is model predictive control. The next level is the planning level. This level uses a computer-based management system called Manufacturing Execution System, or MES. This system monitors the plant from raw materials to finished goods so that management can plan, schedule the production. On top of this, you might sometimes find a management level which uses an enterprise resource planning system, or ERP system, for operational management at enterprise level. There are of course a number of benefits when you compare process control in automatic mode to manual control. The speed and frequency of action is better. So at every sampling instant you have a new MV that is computed. So the variations in MV will be smaller and also the deviations from set point will be smaller. Well, the control action is based on a PID algorithm, so that you take quantitative decisions and they will always be the same under the same circumstances. Of course, you can run several controllers in your PLC so that you can do simultaneous variable changes, whereas an operator is of course limited in the number of controllers or processes that he can monitor. The consequences of process control in automatic mode is that the operator becomes a supervisor and that the productivity will improve and go together with more consistent product quality properties. Well, there is also a big chance that there is a reduction in the energy consumption and an increase in the operation safety. And since when you do process control, you have to do it on the basis of a model very often, you'll improve your understanding of the process. You might wonder why we are comparing process control in automatic mode with process control in manual mode. Well, even in a modern control system, manual mode might be encountered often. Manual mode, except in certain situations such as production startup, is often indicative of a problematic situation. For example, a control that is not tuned properly, a control structure that is not adequate. And what happens is that the operator does not have confidence in the control action and takes the controller to manual mode. These are the desirable features for feedback control. Well, the first feature is not desirable, it is necessary. We have to impose the stability of the closed loop system. The second feature has to do with tracking. We want PV to go to its set point as fast as possible. So when there is a closed loop set point change, well, you have indices like settling time, rise time, and so on. Of course, you have to have an adequate disturbance rejection, and this you can see in terms of variation around the set point. You have to be insensitive to model and measurement noise. So this means that if the process, for instance, changes a bit, well, the process controller should still be able to control the system with adequate performance, and this is sometimes called robustness. It is, of course, important to meet these indices without having an excessive controller action MV. And well, it is important, if the process is non-linear, that you meet these performance indices over a wide range of operating conditions. In practice, it is in most cases impossible to satisfy all 6 features, so you have to look for a trade-off. The objective of feedback is to cope effectively with change. There are 3 main sources of change. The first one are disturbances. These disturbances can act at the input, then we speak of a load disturbance, or they can act at the output, and you have here a list of typical disturbances. A second source of change is a set point change, and this is of course initiated by the operator, or we can have, well, a transition between set points, and then we speak of a tracking of a desirable path. A third source of change is a change of operating point, and this source of change is often forgotten. It comes from the non-linearity of the process. If you change operating point, well, you'll have a change in the dynamics.